look at this. We've got our axis of rotation here. Down here at -3. All right, here we go. I'm going to start out by drawing my rectangle in here. And then to the side, I'm going to redo everything. Here's my rectangle. Here's my x-axis. Here is my axis of rotation. We're about to get to a very critical point here. The bottom one here is the blue one. The top one here is the purple one. When I wrap this, I get a fairly large washer, don't I? It's going to be pretty big. Again, that picture is not that important. What's important is the formula, not the one that we wrote on the board that only works for the x-axis, the more general formula. The more general formula said that the volume of this slice will be equal to pi times, it was the r out squared minus r in squared, then times our dx. See, if it's the x-axis, then this is just the f of x and then g of x. If it's just the x-axis, right? Yeah. But for us, let's look at what is r out. R out is the distance from this to the outer edge, right? That is no longer this distance, is it? It's this distance to here as well. So what you have to account for that. So this distance from here to here is how much? Which one was that? That was this one, right? That's 4x from there to there. But then the distance from here to here is, as an absolute value, as a distance, is what? 3, right? That's 3 units. Which means that the entire distance from here to here, which is your r out, is those two added together. It's actually 4x plus 3. Right? It's not just this distance, it's that plus the axis of rotation distance. Make sense?
So whenever you have to, like, your axis rotation is not around, you know, the x-axis or like that, you're going to have to either add or subtract.
Yeah, and you'll see, because we're going to do another one, we're going to put the axis of rotation above us. So you have to, I don't want you to ever do these problems where you're just like, oh, the axis of rotation down there, I'm just going to add 3. Like, visualize it, because you can make big mistakes when you do that, because it's not as clean as that. You always have to draw the pictures. You can see what's being subtracted from what's being added. Is that a question? Yeah.
So I guess, like, in a sense, kind of like going on what you were saying, like, would you say, I guess, like, since we measure from the top down to the x-axis, then if it goes past the x-axis down, then we add to it, and then I guess, like, reverse, we would subtract from it if it was going further up, if the axis of rotation
Subtract, yes, but subtract what from what? That would be my concern. How would you do it if it's on top?
I would, like, I guess from the axis of rotation to that spot, and then from there down to that x-axis, and then would that be considered the negative?
Yeah, we're going to do that example next. Can we wait on that?
Yeah.
Because I want to let it play out. Because, I mean, this one, we're just going to take that and we're going to add that value. On the next example, we'll put the line up there and we'll see how that changes things. Okay, so that's the outer radius, right? The inner radius is the distance from here all the way down to here, right? That's my r in. And that's going to be, this distance from here to here first, that's x squared, and then this right here again is 3. So this will be x squared plus 3. See, they're different, right? That's different than we had before. The rest of everything is the same, right? You can still set up the integral now. So I'm ready to get my answer. the total volume of this will be the integral pi, right? Remember the pi comes out, pi. Integral from 0 to 4 still. All right, I need my outer radius squared. My outer radius is, 4x plus 3. That quantity squared minus now the inner radius, which was x squared plus 3, but that quantity squared, and then dx. There it is.
Typically with these, because we're doing the pi in front, are you looking for like fraction answers?
And we don't have to calculate these, remember?
For the test?
Yeah, for the test, you're just setting them up.
I thought I heard that.
Yeah. So on a test, what I normally do on these is I give you a region, and I have you wrap it around like 5 or 6 different axes. And then you just give me the formulas for each one. So I'll normally give you a region like this. I'll say, hey, wrap it around the x-axis. Okay, wrap it around a line down here, wrap it around a line up here. And then I'll say that same region, let's wrap it around the y-axis, and then a line over here, and then a line over here. Now we haven't done that yet. That's shells. We'll do that next class. But you know, that's usually the way I do it. And it's just set up the integral, do not evaluate. Set up. So you'll have a total of like 6 integral setups. And that'll be the problem. That'll be the work that you have to do.
So
Yeah.
on the very first graph, you drew a far left, the top left.
Yeah?
If you had drawn that rectangle closer down to the x-axis, would that have changed anything?
No. No, I mean, it doesn't, because even if I drew it over here, do you agree that the distance from, imagine that's, I mean, even if it's way over here, right? Isn't the top of that rectangle still the 4x?
Oh, yeah.
And isn't the bottom still the parabola? Right? It doesn't matter where I am. Yes.
The reason why it doesn't matter is because the integral is going to add them all up anyway.
That's right. The integral is going to add them up, right? You think about the integral as saying this. Because x is the variable here, we're going to start at x being 0, and we're just slide across all the way to 4, and just add up all these washers as we go across. All right, let's do the same exact problem. This time, I want to wrap it around y equals, I'm going to have to go pretty far up there. Let's go to y equals 20. Because where did they hit each other? Where did those graphs hit each other? The x was 4, but what would the y be? 16. So I need a line above it. I will never give you a line, an axis rotation in the middle of your region, because then you have this problem of it rotates on top of itself. That'll never happen. Your axis of rotation will always be outside the region. All right, so do I need to write it down? This time, you know, we're going to rotate about y equals 20. So now your picture looks like this. You've got your parabola over here. We've drawn this region several times now. Like that. Your axis of rotation is up here at 20. I draw my rectangle. I'm going to transfer everything over to the side again, just so I have it. When you draw your rectangle on the side, like I've been doing, I recommend you always put your axis of rotation, and the rectangle. Those are the things you need. The axis, so the x-axis is going to come over here. Your rectangle. Your axis of rotation. This line is on top. This is on bottom. The washer, are y'all following me? Yeah. The washer is like up there. I'm actually off the graph there. It goes way up there, right? Like that. It's up there somewhere. Whatever. You get the idea. It wraps like that, yes? All right. So, guys, I'll let y'all, since y'all have a conversation going on. What's R out?
Well, that's what I was trying to figure out.
Yeah, R out is gonna be the bottom function, right?
Well, just in terms of the picture, the outer radius is the distance from, and y'all pay attention to my language here. The outer radius is the distance from the axis of rotation to the outer edge of the shell, or sorry, the washer, right? It's that distance. It's a distance from this red dotted line to this bottom piece here, which over here is this to where?
The blue.
To the blue. To the blue. That's R out. Everyone see that? R out is the distance from here to here. So I'm going to draw it like from here all the way to here. That's R out.
Would you say it was the greater distance from the axis of rotation?
I like to look at it actually like I'm physically a person standing here. That's my head, and I'm looking this way. Those are my eyes. Okay, and I'm looking out, and I'm going from the axis of rotation to the outer edge, the rectangle. Like I see a rectangle on the ground over there, and I'm looking for the outer edge of it, right?
So if the axis of rotation is above the region, then the bottom function is going to be the outside radius.
Maybe. I don't think of it that way. I actually just try and look at each problem as its own, like I'm just trying to figure out what's R out, what's R in. I don't want to make it like if this scenario, then do this. I think it's better just to think about each one as like just find R out and R in. Just imagine you're standing here. What's the distance to here, right? Where do you see where R in is? Like, do you see it? It's from where to where?
From the axis to the purple.
Purple. There. That's R in, right? The problem with trying to like get scenarios is that can catch up to you because you start to have all these, you're going to have like 20 scenarios, right? That you have to try and remember, oh, if it's this, then do that. If it's that, then do this. Just each problem, draw the picture, figure out what R out is, figure out what R in is, and then you're in business. Now let's get R out. We're not done. We know what it is like on the picture, we know what it is, right? But what is the actual distance? So the distance from here to here is what? 20, always, right? Because that's 20 and that's the x-axis, right? So that's not changing. So R out is not 20, it's actually less than 20. How much less? Well, that much less, right? It's that much less. So you have to take 20, which is this whole thing, right? That's 20. The distance from here to here is the bottom one, x squared, right? So R out, what did you say? It was 20 minus x squared. It's the full distance, 20, knock off the x squared, and that'll take you to the R out.
How do you know that was x squared?
It's the blue curve, the bottom of this, which is this, right?
So would the R out be 20 minus x?
Yes, that's exact, yes. Do you see it? Do y'all see it? So R out, you good over there? Yes? Okay, this is 20 minus x squared.
Is there positions in the equation reverse? Because
Nope.
you're using
The formula is always R out squared minus R in squared. Always.
right. But
So-
the R out here is changing because we're
Nope.
talking about the blue rather than
We're talking about the distance from here to here. Doesn't matter where we are. We're talking about the distance from here to here. The reason why it's not going to matter is because you do R out squared. So the position, the relative position of where you're looking from doesn't really matter because when you square it, you get the same result. What about R in? What about the distance from here to here? Yeah, it's not the full 20, right? You have to knock this much off, right? You have to knock that much off to get to R in. So that's 20, and you need to subtract from that this, which was what, 4x? So this will be 20 take away 4x. In my experience with this idea, right, in calculus 2 and people taking tests, students who try to come up with like, okay, if the line's above, I'm gonna just flip it and then subtract or something. without actually having the visual picture are the ones who get it wrong on the test. Normally, that's what happens. Because they try and get into like not really seeing it and just hoping that they're getting everything in the right place in their minds. Does that make sense? That's usually when students make mistakes. Look, a lot of us are engineering, you know, we're all STEM in here pretty much. Everyone's some sort of STEM. Visualization is an essential skill. I mean, you have to be able to see things, right? And then turn that somehow into the math. So if right now this is still like kind of in your mind a little bit kind of blurry, it's okay, but we want to get to the point where this all like makes perfect sense. Okay, ready for the formula? Pi, integral, 0 to 4, that doesn't change, right? Outer radius squared minus inner radius squared. Outer radius is 20 minus x squared, and then you take away the inner radius, which is 20 minus 4x squared. All that dx, we're done. That's the setup.
So what are the two equations actually again?
What are the what? The outer radius squared, inner radius squared.
No, I mean, what's that? That's how much you get.
Oh, I didn't put it up here because I think this is like the third one we've done. It's 4x. The purple one is y equals 4x, and the blue one is x squared.
For the exam, I know you don't need the exact answer, but you're also okay if we don't just break down that parentheses. Just leave it just like that. You don't have to like, yeah.
Just like that.
Okay.
Yeah, on the exam, I prefer you just to leave it like this because it's easy for me to grade. And then if you do FOIL it out or something, make a mistake, then I have to take off.
Right. Yeah.
You know, so like just leave it in the safest form possible right there. Yeah.
You still want us to like kind of show the
Oh, I want pictures. On the test, I want pictures. Oh yeah, I want drawings.
So,
All right?
Just to be clear, we got kind of lucky with this example, these three, because we were able to look at it and tell what the integral, like, from 0 to 4. But like normally you would have to set like the functions equal
Yes.
to each other.
Uh-huh. Yeah. But that's what we did in 7.1, right? The previous section? That's what we did. So it's not, we're just, you know, adding a little bit more. All right, we still have time. I have 15 minutes. I think maybe we've done a region that's wrapped around x-axis and then a line below and a line above.
What about like other quadrants? I don't know if that's it.
What about like?
I'm going to stay in the first quadrant.
What about if like we're doing it horizontally, the box?
Oh, there's an rectangle.
Yeah. So I'm trying to decide now, should we dabble into the next method or should I?
Are we gonna be like doing anything over the line y equals x?
Let's do this. This is just to show you the power of what we now have. I think this will be a good way to end the week. A quiz. Let's do a quiz, yeah.
Find the area. Now find the area.
Okay. All right, so here we go. This will be interesting. Show the volume of a sphere of radius r, capital R, is 4/3 pi r cubed. If you look at your formula sheets and you look at the formula for the volume of a sphere, you will see this formula for the volume. So if you take a sphere, a solid ball, if I call the radius of that sphere capital R, looking on your formula sheets, you'll see that the volume is 4/3 pi r cubed, right? Prove it. Prove to me that that formula is right. Like, show me where it comes from. Where does the formula come from, right?
The integral of 4 pi r squared. I mean, just looking at it.
It's the integral of 4 pi r squared. Yeah, you could, with respect to r, you could, yeah.
I don't know what that means.
Yeah, I mean, yeah, you could. You could also say that that's the integral of 4/3 pi r cubed with respect to x. Like, you know what I'm saying? Like, there's a yeah, okay, yes. I know where you're going. Let's move to something else. All right, so here we go. This is going to be a little bit crazy, but I think the end reward is that we get to prove the formula, right? So I'm sitting here, I'm going, how in the world am I going to do this, right? How am I going to prove that this is true? Well, now I have this idea that I can rotate regions around axes, right? So can't I just take, if I want to keep it real simple, can't I just take like the first quadrant of a circle of radius r? Let's say that's a circle. Imagine a circle that goes all the way around. If I just look at the first quadrant of that circle, if I wrap that around the x-axis, if I wrap this around, don't I get half of this?
Yeah, you do.
I do. I get half of that, right? So why don't I just try and wrap that around the x-axis, and then whatever answer I get, I'll double it, and I'll see if it comes out to be this. Make sense? Wrap that? Yes? Now, to do that, I need to actually know what the equation is. And I should probably stress also, we have a top and bottom function. The bottom function is actually just the x-axis itself. Right? So my rectangles are going to be in here like this. And I'm going to wrap. Yes? But we need to know, what is that top function? What is this top function? Well, the problem is a circle is not a true function, right? Circle fails the vertical line test. So reminding you, the equation of a circle that you center at the origin is x squared plus y squared equals the radius squared. That's the generic formula for a circle. For us in this picture, it's capital R squared. Do y'all believe me? This is the equation of that circle. But this equation would actually draw the whole circle, wouldn't it?
Yeah.
Now, if I want to look at this as a function, I'd have to solve this for y. So I would have to move things over. Subtract x squared on both sides. And then I would have to take the square root. And this is where we run into a problem, because when we do square root, we have to do plus or minus, don't we?
Yeah.
But I'm only going to be looking at the top half of this. The top half is drawn with the positive answer. The bottom half is drawn with the negative. So I'm only going to be looking at the top half, square root of r squared minus x squared. Like that, right? All right. Does everyone buy this, that y equals the square root of capital R squared minus x squared is the formula for this function here on top? Yes? And the bottom is, what's that bottom function? Y equals 0. Okay. Let's wrap it around the x-axis. Let's wrap that around the x-axis. So come over here, axis of rotation. Your rectangle is actually just that right there, right? It's just boom, like that. Wrap that around, and when you wrap it, you actually get a cylinder, don't you? Not a washer, because there's no hole in the middle. And so I can just come up with a formula of what's R out, what's R in. What's R out?
It's the square root of r squared minus x squared.
Yeah, this right here is R out. It's just that top piece right there, right? Which is this right here. Square root of capital R squared minus x squared, right? And then what's R in? 0. Yeah, it's kind of weird, but it's like R in is 0 because it's the bottom function, which is 0. All right, just go to the formula now. The volume of this should be integral from, be real careful here, integral from where to where? 0 to capital R, right? That's where we're going to stop. And then it's going to be the outer radius squared, thank goodness, right? Take that and square it, which kills the square root, which leaves you with R squared minus x squared, right? Minus what? 0? So just this dx. Oh, thank you. I forgot the pi. That would have been a problem.
That would also be equal to 2 times the radius of just the top half.
2 times the radius.
Well, if we multiply that by 2, it would be.
Oh yeah, we could have gone from negative r to r and gotten the whole top half, or we could have just gone from here to here and then doubled it. I'm going to look at this as just this being wrapped, and then that answer is half the volume of this, right? So I'm going to double it at the end. Okay, can you do that integral? It may look bad. It's not bad at all. It's actually really, really simple integral. Okay, this is equal to pi. Okay, antiderivative time. What is the antiderivative of r squared with respect to x? So r is a constant, right? So it's r squared x. R squared x. The antiderivative of this is r squared x minus, okay, what's the antiderivative of x squared? 1/3 x cubed. And then we're done, right, with the antiderivative. We evaluate that from 0 to capital R. And so let's plug in capital R first. We're going to get 2 answers here, right? We're going to do this minus this. If you plug in capital R for x, let's see what happens. We have the pi out here, right? Capital R goes right there, r cubed, minus 1/3, r cubed again. Okay, now minus, plug in 0 for x, kills both of them off, doesn't it? 0. I don't like that. I used a bracket, then I used a parenthesis. That's kind of... Okay, there.
No, this is the part.
This was a pi. There was a pi out here, but it didn't matter because there was a 0, right? So this is getting mixed in there.
So that's just nothing, right?
This is nothing, right? So at the end of everything, I have the pi out front. Then I have r cubed take away 1/3 r cubed. So that's 2/3 r cubed. And that is my answer. But I double this answer to get the full volume, right? And if I multiply this by 2, look at this. Right? Just multiply that answer by 2, and all it does is just makes that 2 on top become a 4. Remember, we took just this quadrant, we wrapped that around. When we wrapped that around, we just got half of the sphere. And so we have to double that answer to get the full sphere. I bet you never thought that I'd be able to prove that formula to you in less than 8 minutes, right?
Yeah, I think what threw me off was that height for R.
The height.
When we do the integral from 0 to R.
Oh yeah, our limit of integration, it goes from 0 to the radius, right? Because the circle ends at R, capital R, because it has a radius of capital R, right? That's actually pretty simple to, I mean, I'm not going to, it's pretty straightforward. Once you understand like how the volume formula works, it's pretty straightforward to prove that formula, isn't it? There's another one, we have 5 minutes, I'll show you this one. This one's a much harder problem. In the past, I've given this as bonus, but I'm not going to offer it as bonus this semester. There's 2 formulas. I'm going to show you how it would go, how you would do them. First one is, what is the volume of a right cylindrical cone? Right? So if you look this up on your formula sheet, the volume will be, like if this is R right here, and you have to know the height. It's going to be 1/3 pi r squared h. That's the formula for a cone. Which if you think about this formula, if you take away the 1/3, that's the cylinder formula, right? So what we're saying is that a cone is actually 1/3 of what it would have been if it had been a cylinder. Which kind of intuitively makes some sense, maybe, I don't know. So the way you could prove this formula is to do this. Draw just a line that goes from here to here. And imagine wrapping that around the x-axis.
Yeah.
Right? Now the question is, what is the equation of that line? Like, what is that line? So I actually do have 2 points. Can someone tell me what this point is? That's h0, right? Because the distance from here to here, that's the distance from here to here. That's h0. And then what's this point right here? 0r. And if you have 2 points, can you find the equation of the line between 2 points? Yes. So there is a way, doing a little bit of algebra, that you'll be able to tell me exactly what that is, right? And then you will have the top function. And the bottom function is 0. And then once you have the top and bottom functions, then you just go to the formula. And if you work that out, I promise you get 1/3 pi r squared h. A more complicated and more difficult problem is to find the volume of a frustrum. A frustrum, which is...
Is it because it's frustrating?
It's frustrating, yeah. It's a cone with part of it cut off the top. And with this, you have to be given two different radii. You have, let's say, R2 here, and you have R1 here, and then the distance from here to here we call h, right? And there's a formula for this, and I actually don't know the formula off the top of my head. But I could find it. Without a book, I could find this, because I could set up the integral for it. Yeah, all you do here is just move this line piece right here. Now, that sounds easy, but it's a little bit complicated, because imagine I do that. Okay. It's just a little bit harder. If I do that, let's see. What is this point right here? 0. It's the R2 one, right? The bigger one? And then that one is HR1. Now that doesn't seem that made much of a difference, but it actually does have pretty big impact on how nasty the integral gets, how many things you have to keep track of. Because see with this one, like here the x coordinate's h, and that's 0, here it's 0, and then that's r. So when you do your slope, it's a real nice slope, right? What's the slope of this line? How do you find the slope? I'm out of time. Rise over run. So it's the difference of the y coordinates. So that minus that, like negative r over h. Okay, that's the slope of that line, right? And then what's the slope of this line? It's a little worse, right? A little worse, not terrible, but you know, it's r1 minus r2 over h. But then that's just the slope. You have to find the equation. I'm not going to go through it, but do you see how you really can think of it, a lot of the geometric shapes that we have, three-dimensional shapes that are useful in the real world, we can find the volumes of all of these just by wrapping certain shapes around the x-axis. So, kind of cool. They are derived in many different ways, but this is a nice way to derive it. Yeah. Okay, everyone. I would say start your homework for the 7.2. All right, because 7.2 is just washers. I will warn you, though, that if you see any problems where they ask you to wrap around the y-axis or x equals a number, just ignore that because we haven't done that.